the units we're looking to cover, okay? Physics deals with the behavior and structure of matter. So would you think that physics is going to be a life science or a physical science? Physical. It's a physical science, hence the name physics, okay? It's a physical science, so it deals with matter, it deals with energy, it deals with molecules, things like that. So behavior and structure of matter. There's lots of different topics within physics that we could choose to study. Okay? In high school physics, basically this class, this honors physics class, will essentially get you through one semester of college physics. Okay? So our year will essentially get you through one semester of an advanced physics class in college. Okay? Or of a classical physics class. And that's just the topics. College physics obviously dives a lot deeper into those topics, and it's calculus-based most of the time. This is still algebra-based. But the equations don't change, okay? So this class will kind of get through a few of these topics, not all of them on the list. We deal with motion almost entirely, especially in the first semester. We get to heat a little bit. We might get to light. We might get to sound a little bit. We don't really get into magnetism, electricity, or fluids. Okay, we spend a vast majority of our time in this class talking about motion and objects that are in motion, moving from point A to point B. We'll deal with objects that are spinning. We'll deal with objects that are rotating. We deal with objects that are in orbit. Okay, all of those things are still considered part of motion. So we kind of take that motion topic a lot of different directions, but that's going to be the main focus of our study. Toward the end of the year, we'll get into simple harmonic motion, things like pendulums. We might get into light and waves and vibrations and things like that, but we spend a vast majority of our time on the motion spectrum. All right? So what's the point? Why do we bother studying it? Okay, why do we study science and the physical sciences in general? Okay, the reason we study science is we want to find patterns in this world around us. Okay, search for order in our observations of our world. So, does anyone remember the term for disorder in chemistry? What's that called? Entropy, right? The amount of disorder in a system is called the amount of entropy it has. Okay, so here we've got a world full of disorder. And physics kind of allows us to search for patterns and try to find order in all of this crazy thing. Okay, we're trying to look for patterns in motion. We're trying to look for patterns in vibrations, waves, all that kind of stuff. Okay. While we're making these observations of the world around us, we have the opportunity and we start to understand these different phenomena. We develop models and theories and laws. Okay, and we should kind of have an idea what each of those three things are, but I'm going to talk through them just real briefly here. Okay, we develop models and theories and laws. An analogy, it can be a mental image, it can be something that's built. Models can be understood lots of ways. Okay, we try to model things basically to copy something we already know. Not copy necessarily, but we try to visualize it in comparison to something that we already know. So the Rutherford model of the atom is also called, anyone have any idea? The Rutherford model of the atom is also called the planetary model. Okay, because it's got the circular rings, kind of looks almost like Saturn. Okay, it's called the planetary model. They tried to name that model after something we were already familiar with, okay, to give us a better visual of that. All right? When we work on physics problems, we're gonna depend on using models a lot. I'm not talking about three-dimensional models necessarily. I'm talking about just little diagrams that describe the motion of an object. Okay, so if I give you a problem that says, I threw a ball up into the air. We want to see how high it's going to go, then it's going to come back down. So here's my ball. I'm going to throw that ball into the air, then it's going to come back down. I just developed a model, right? All I did was draw this simple picture of what's happening in my motion. Models like this, as simplistic as they are going to help you solve a lot of problems. Okay, so I would really, really encourage you to draw these types of pictures when we start looking at these problems in terms of vertical and horizontal motion. They're going to give you a lot better idea about what's happening in that segment or that little time frame that we're looking at. All right, so it can be as simple as this. It can be as complex as the planetary model. But models can be used for lots of different things. Okay, so essentially what models do is they give us a mental or a visual picture. They're telling us what's happening in that scenario or that problem. All right, so we have models, theories, and laws. Theories are similar to a model. They give us broader and pretty detailed descriptions that become testable predictions. Okay, so I know it seems counterintuitive to say it's broader but more detailed, but that's the truth. Okay, it's over a big topic, but it has extremely detailed descriptions. Okay, theories give us the ability to test something. They give us a prediction about what's going to happen. Then we can follow through with the experiment or the test. Okay, so things like atomic theory, things like the wave theory, those give us testable predictions. This is what we think is going to happen, and this is what they've told us is going to happen. This is what's been tested, or maybe it hasn't been tested yet, but we've got this theory. Okay. All right, last but not least here about these models, theories, and laws. Laws are certain. Okay? They have been tested over and over and over and over again until basically no one has disproved them. Okay? Can we say they are absolute? Probably not. But they've been tested and tested and tested, and yet no one has been able to disprove them. Okay, so we consider it a law at that point. There's no certain amount of tests. It's got to reach 100 experiments or 1,000 or 10,000 experiments before we can consider it a law. They've just kind of essentially become accepted, right? We've tested and tested and tested. No one's even come close to disproving them, so we then consider them a law. Okay? So major laws are the conservation of energy, conservation of mass, things like that. Those things have never been disproved. Okay, we test them over and over and over again, never been disproved. Newton's second law says force equals mass times acceleration. That's a conservation of energy equation. And laws, in order to be called a law, have to be found experimentally valid. Okay, they have to have a certain amount of validity. Essentially, they have to be they have to be proved and proved and proved, or not disproved over a certain time. Sorry, did you have what you need? Okay. When we talk about physics measurements, we're most of the time talking about a distance. We're most of the time talking about time. We're talking about speed or velocity. Those are all types of measurements. Okay? In physics, we're not so concerned with usually mass. Not usually so concerned with mass. We're not usually concerned with, what are some other types of measurements that we might take? Anyone have any other ones? Okay, I already named them all. Most of the time we're looking at distance, time, and speed. Okay, we can put those two together to make speed, but all right. When we take a measurement, we don't ever have an absolutely precise measurement. There's always some level of error that goes along with it. Okay, an error or uncertainty that goes along with my measurements. Okay, and the uncertainty, the amount of error, the amount of uncertainty is usually given to us on our measurement device. Okay, so my meter stick might say, this meter stick is accurate to 1 millimeter plus or minus 1/10 of a millimeter. Okay, so that's telling me these marks are pretty close to a millimeter apart, but there might be a little variance. Okay, so we have to take into account that uncertainty and that error when we take our measurements. The other thing that can give us a little bit of error in our measurements, and the most often, is human error. Okay, so some people just can't read measurement tools very well. If you're one of those people, you might let your partner do it. Okay? Human error is by far the most accounted for error in your measurement system. Okay? Measurement tools are made to be extremely accurate, but human error is where we get off a little bit. Okay? So if you're doing an experiment and you have to take 5 measurements, is it best to have all 5 people in your group take one measurement, or is it best to have one person take all 5? One person to take all 5, and why is that?
Because sometimes read it the same.
Exactly. You're going to have more consistent readings by having that one person view the tool 5 different times. Okay? Because I might be at a different eye level than somebody. I might have different eyesight than somebody. So at least with one person reading the tool the same every single time, you eliminate one version of human error. Right? So we're not having 5 different views looking at that measurement tool. All right? Some measurement tools have more error than others. For instance, if I wanted to, let's say, go into the chemistry lab, and I wanted to measure 100 milliliters of water, would I get out a beaker and put in 100 milliliters? No. In the chemistry lab, right, I would choose a graduated cylinder, or I would choose a volumetric flask. I would choose something that's made more specifically for the amount that I need. Okay? Just like if I wanted to measure how long my fingernails were, am I going to go get a meter stick? No. Okay? Definitely not me. Okay? I'm not going to go get a meter stick. I'm going to go get a little tiny thing because I don't have any fingernails. Okay? You just have to pay attention to what you're going to measure. If I need to measure the length of the hallway, am I going to use a ruler? No, I probably want to use a meter stick in that case, or a tape measure or something like that. I'm not going to use a tool that's going to account for more error. Okay? Because if I go measure the hallway and I use a ruler, every time I move that ruler, I have to tack on more and more error. Every time. Plus or minus 1 centimeter, plus or minus 1 centimeter, plus or minus. I mean, my error just adds up. By the end of the hallway, I'm probably a whole foot off. Okay, I could be almost 20, 30 centimeters off. Okay, so you just have to pay attention to picking the correct tool for the thing that you want to measure. Okay, we got some new timers in our labs that go with the computers. So those are going to be a lot more accurate timers than trying to use like a stopwatch or a phone or something to do our timers with. So we've got to choose the appropriate tool based on what you're trying to measure. Okay? All right, so let's talk about the difference between accuracy and precision. Does anyone know the difference between accuracy and precision right off the bat? I know, this one's tricky. It's always, you know the definitions, you don't know which one goes with which. Okay? Accurate is close to the actual. Okay? Accurate is close to the actual. All right, so let's say that I am all right, let's say that I am going to be looking at a target, which I'm trying to draw a pretty target here. It's not really working. That's pretty dang close. Okay. All right. That's a pretty good target.
That's really good.
All right. I mean, granted, I have a circle tool, but still, that's a pretty good target. Okay. So let's say that I'm trying to swing at a target, and I have, let's say, 10 attempts. Okay. So let's say attempt here is there. Okay, my attempts are kind of all over my target. Do I have one pretty accurate attempt? I have one, maybe two, but really one pretty accurate attempt. But these measurements are all over the place. Okay, so I could say, yeah, I have a little bit of accuracy, But on the other hand, I don't have any precision. Okay, so let's look at what precision means. So I might have one accurate attempt here, but I don't have very much precision. Okay, so precision is going to be how closely related our measurements are to each other. Okay? And let me redraw my target here, see if I can do that again. Okay, so there's my 10 measurements this time. Are they accurate? No, but are they precise? Yes. They're really close together, but they're not close to the actual. It's not close to really what we want, but they're all very precise. Okay? So when I'm measuring my values, I want my average to be as close to the actual as I can. Here my average leads me all up in this upper right quadrant. Not very accurate, but very precise. So in an ideal world, when I'm looking at my averages, I have both precise and accurate measurements. Close to the target and all close together. Okay? So where I would want to be with my range is in here. Right? I want all my 10 shots to be accurate and precise. Does that make a little bit more sense with the bullseye? Mm-hmm. Okay. So think about that. Accurate is close to the actual. Precise is how close they are together. We want both. Okay. There's a couple different ways that we can have error in terms of accuracy and precision. Okay. So we could be incorrectly reading a measurement or a tool, an instrument. But if we incorrectly read that tool over and over and over and over again, would our measurements be precise or accurate? They might be really precise, but they're wrong. Okay, so if I'm measuring something that's 58 centimeters, but I keep reading my tool as 68 centimeters, right? 68.1, 68.02, 68.13, and it's really 58. My measurements might all be really precise, but they're 10 centimeters off, right? So if I'm misreading an instrument, I might have really precise measurements, but not very accurate. Does that make sense? Mm-hmm. Okay. To ensure we have the same and good precision, we want multiple readings by the same person. We already talked about that. Okay. If we're ever asked to calculate percent error, how many of you have seen this equation before? Good. Percent error means we're taking basically the difference between the experimental and the accepted value, but we're always dividing by the accepted or the actual value. These two lines on the outside of our equation mean what? Absolute value. So we're never going to have a negative percent error. So realistically, it makes no difference what you subtract by on the top, which one goes first. Okay, it makes no difference there because people get confused about is it accepted minus experimental or is it experimental. It doesn't matter which one you subtract by on the top as long as you divide by the accepted value. Okay? Because either way, you're going to get the same number on the top. It might be positive, might be negative. But we have absolute value anyway. Okay, so it doesn't matter what you subtract by on the top as long as you divide by the accepted or the actual value. Okay, so experimental is what you get. The accepted or the actual is what you're supposed to be getting. All right? Understand there? Okay. So you need to have that equation in your notes. You'll use that every once in a while in here. Okay. Significant figures. Everyone's favorite topic, right? Are significant. Okay? So any basically non-zero digit is always significant. Okay? If you are good with significant figures, you don't have to bother writing all this down. That's up to you. If you need a little refresher, go for it. Because I know it's usually the first thing covered and not ever again. Okay. So all digits that are not zeros are significant. So in this first number, 23.21, how many sig figs do we have? 4. Okay. In our second number, how many significant figures do we have? 2. Okay, 2. These are zeros to the left of digits. Any zeros to the left of digits, whether it's before or after a decimal point, are non-significant. Okay, that decimal point is just a placeholder. Okay, so these two zeros are non-significant. All right. All right, what about our last number here?
3.
We have 3. 1, 2, 3. Okay, so these are leading zeros. We don't have any trailing zeros here, but non-zero digits are significant. Zeros to the right of digits after the decimal point are also significant. Okay, so non-zero digits we just talked about. Zeros to the right of digits after the decimal point are significant. So if I write the number 7.000 centimeters, how many significant figures?
1.
Yep, we have 4 here. Okay. The reason that we have 4 is because those 3 zeros are telling us it's exactly 7 centimeters, and that we measured it out to 3 different decimal points. So our measuring device measured to 2, and we guessed that last digit, and we still think it's a 0. So that's all significant. Okay. So that 0 to the right of the decimal point is significant. Okay? It's telling us it's exactly 7.0 centimeters. All right. So if I ask you to write a measurement with 4 significant figures and you know it's 7 centimeters, you can just give me those decimal points. Okay, that gives me 4 significant figures by having those decimal point and those zeros. Okay, so zeros to the right of the decimal point after digits are significant. If I give you this value, 0.00080, how many significant figures? 2. Good. 1, 2. Okay. This 0 is to the right of digits after the decimal point, so it's significant. These guys are just placeholders. We could have put it in scientific notation. Okay, so that's telling us this 0 right here is telling us something important. These are not. Cool? All right. Zeros to the left of digits are non-significant. They're placeholders for the decimal point. Okay, I know we've touched on this a couple different times. So zeros to the left of digits, right before any digits start, are non-significant. All right, so that example I give you right here, 0.0860. Oops. How many sig figs? 3. 1, 2, 3. This 0 is to the right of digits after the decimal point. This is to the left of digits. Doesn't count. Same as this one. That's non-significant. Zeros between digits are significant. Yeah, that's one of our next rules. Good question. Zeros between digits. Claire's one ahead. There we go. All right. Zeros between digits are significant, because that's just kind of part of the number. All digits used in scientific notation are significant. So what I mean when I say digits used in scientific notation means the ones we can see. Not if you expand it out of scientific notation. The ones we can see in scientific notation are significant. All right, scientific notation. Please tell me everyone here is like 100% on scientific notation. Yeah, feeling pretty good about that? All right, I hope so. Okay. So scientific notation, if I give you 2.40 times 10 to the 6th, how many sig figs? 3. All those digits that I can see are significant. Okay? It doesn't mean that I want you to expand it out I don't know how many zeros goes with this there. Put the in the wrong place. I don't need all those zeros. Those aren't all significant. Just the ones that we can see. So we've got 3 significant figures. Okay, I don't want you to expand it out and try to count from there. All right, if I gave you 1.0010 times 10 to the 5th, how many significant figures do I have? How many? Yep, good. 5. Right, anything visible in scientific notation are significant. Very good. Some numbers are ambiguous and we're not sure how many significant figures we have. Can anyone give me an example of an ambiguous number? There's lots and lots and lots. Yeah, okay, pi, yeah. Yeah, I mean, not what I was thinking of, but sure. Yeah, I mean, you can stop pi at any point, but yeah, you're right. We don't really know how far it goes out. Yeah. Okay, anything else? Okay. Sure.
It's like 100 without a decimal point.
Yeah, there we go. That's what I was thinking of. Things with trailing zeros. Good. So 120,000, 10, 200. Those things have trailing zeros. Okay, I call them trailing zeros. I don't know if that's the real name. They have zeros at the end, but no decimal point. We're not telling us, is it exactly 120,000 or is it somewhere around 120,000? We don't know. Okay, it could be 120,000 with 3 decimal points, which would mean it's exactly 120,000, or it could be 18,945 and we're rounding up to 120,000. Okay, so we're not really sure where it lies right there. Okay, so that's called an ambiguous number. Anytime we see zeros at the end, we consider it an ambiguous number. Okay. These are the ways that you can fix ambiguous numbers. So this is something for sure I want you to have in your notes. Okay, use scientific notation or add a decimal place to correct an ambiguous number. I don't like when you hand in ambiguous numbers, right? If we're looking at significant figures and specifically I'm asking about significant figures and you give me 20 or 10, that's an ambiguous number. That's not telling me how exact it is. Okay? So if our measurement is somewhere in the 120,000 range, which would be a better fix for this ambiguous number? Scientific notation or adding a decimal? Yeah, scientific notation. So I might say 1.20 times 10 to the 1, 2, 3, 4, 5. Okay, because that's telling us it's around that 120,000 range. We're not sure where in that range it lies. Okay, that's what that's telling us. If I wanted to say it's 120,000 on the dot, a decimal points might be a better option. Okay, so I might say it's 120,000.00. Okay, depending on how exact it is, I could add as many decimal points as I want. That just keeps adding significant figures. That makes sense? So you can vary the amount of significant figures you need to display in scientific notation. But if you wanted to show an exact amount, you would add a decimal point and add a 0. Okay? Something to point out here is that adding just the decimal point and no 0 on the end, so if you just say 120,000 and then you just put a point, that doesn't do any good. Right? You have to add at least a 0 there. Okay, because just adding the decimal point, it's not like the end of a sentence. You just get to like put this dot and then you're done, right? So you have to add a 0 there, so that adds a significant figure. So when you're looking at how many sig figs you have, you can't just put the dot and call it good and say, all right, I only got 6. Really, when you add that decimal point, you then add a significant figure, which means you have 7. Cool? All right. All right, very good. All right. Math rules, everyone's favorite. So first one is if we multiply and divide. I don't ask you for significant figures very often. Realistically, once you understand the rules and can show me that you've mastered them in the first chapter, once we get past that, I'm not too concerned with significant figures. It's not something that you're going to have to show me on every test and everything throughout the rest of the class. I'll be honest about that. Okay. Some classes when you get in college will expect perfect significant figures throughout the entire year. Okay, so in my physics class in college, I had to have perfect significant figures, and I got counted off on every single lab, every single thing I did ever, because I never could do significant figures right. Okay, I don't think I mastered significant figures until I had to come here and teach it. Okay, I'll be honest. Until I had a student teach it, until I had to come here, I just didn't get it. I don't know what the deal was. It was not happening for me. Okay, so some teachers will really expect you to have that significant figures present on every single assignment, every single answer you give. I don't really have that expectation. Okay, so at the beginning we'll hit significant figures pretty hard. After that, just kind of keep it in the back of your head, things like that. Okay, but for right now, we're looking at rules for multiplication and using our significant figure rules in multiplication. You're looking at the fewest number of significant figures. So your answer should only have as many significant figures as the smallest amount that you have. Okay, I know that sounded a little bit jumbled. You can only have as many significant figures as your answer as the fewest number you multiplied with. Okay, so if you've got this problem right here, we look at our, I don't remember what, the first one has how many significant figures? 3. I keep doing this. 3 significant figures. My second one has only 2, which means my answer can only have 2 significant figures. Right now it's got 4. How can I change that to only having 2 significant figures? I'm going to round, and I'm going to round up because this 84 rounds up. So my answer can be 77 centimeters squared. There's another way I could change that to the correct number of significant figures. Any idea? Scientific notation. So scientific notation always works. And can I do 7.684? No. Can I do 7.68? No. I have to do 7.7 times 10 to the what?
Whatever they said.
Times 10 to the first. I want my answer to be 77. Okay? If I take it times 10 to the third, if I would take 7.7 times 10 to the third, that means my answer would be this, 7,700. Okay? That's something that trips people up with scientific notation a lot, so I want you to be careful about that. We want to look at the decimal point that we have. We move it one place from 7.7 out, so that means it's only 10 to the first. Okay, so be careful about that because that trips a lot of people up. They want to say go all the way to the end. You're only going to your original decimal point. So our original decimal point was between the 6 and the 8. All right? So 7.7 times 10 to the first, or just round to 77. Okay? All right. When we add or subtract, we're looking at decimal points, not significant figures. Okay, so when we add and subtract, we're looking at decimal points, not significant figures. So when you do the math and you do order of operations, you should go multiplication, division first. Use those significant figure rules. Then you can do addition and subtraction if you have to, and you'll change and use this other set of rules. Okay, so multiply and divide, you're looking at sig figs. Addition and subtraction, you're looking at decimal points. Your answer has to be the fewest amount of decimal points that you started with. All right, so in my answer, I'm going to look at, so our first value has how many decimal points? 1. Okay, remember, not significant figures, decimal points. 1 decimal point. Our second value has 2. So that means our answer can only have how many? 1. 3.03. So I'm going to round that to 3.0 centimeters. Okay, we have to include units on all of our answers. That's something that you're going to have to get used to in physics. Units are going to be a big indicator for us about variables. So you have to tell me what units go with them. Okay? Units are so important. All right, we're going to keep booking here. Look at SI units real quick. SI units and prefixes, everyone's favorite things. Hopefully this is the second or third time you've seen them at least. Okay? So if you like, you don't have to write all of this stuff down. I know you've seen it before. But we're going to talk about SI units, or otherwise known as the metric system. Good, the metric system. Okay, so in the Olympics, are you guys noticing that they're using the metric system? Okay, so the reason that we have to know the metric system is because basically every other place in the world uses it, just not us. Okay. These are base units, so if you don't have these, if you're not familiar with these, I want you to go ahead and put these down. You don't need the bottom three. You don't necessarily need these ones. We won't use moles any in here. So you need to know length, mass, time, and temperature at least. Okay, you need to have those top four. If you don't know the base unit and the symbol for those, make sure those are in your notes. The length unit's meters. The mass unit is kilogram. Time is seconds, and Kelvin is K, which is a capital K. Seconds, make sure it's just an S, not SEC. Does anyone have an idea why the unit, the base unit for mass might be kilogram instead of gram? Grams are really small. So measuring any sort of realistic amount of substance is most of the time done in kilograms. Okay? So when we're looking at prefixes, the gram would still be the base. But when we're talking in terms of base units, things that we should normally measure in, we're looking at kilograms. Does that make sense? So kilo is still a prefix. On the conversion chart, gram would still be the base line. Kilo still is a prefix there, but that's our base unit as part of the metric system. All right, do we have what we need here? All right. SI units are on a scale of 10. They make conversions really easy. So I pulled up a new conversion chart that I like better, okay? Because I think there's a little bit easier way to do these conversions, at least for me. Maybe not for you, but for me, this is a little bit easier. So I'm going to kind of explain what this chart's telling us. These ones in red here are the ones I would like for you to be really familiar with, and nano. So down to nano, okay? The reason that I like this chart better, for the most part, is because it's telling us how many meters are in that particular substance, or not substance, prefix, okay? And it works for the top ones. Once it gets to the bottom ones, I want to show you kind of how I flip those a little bit, okay? So once you get to like here, once you get to about this point, I want you to maybe just pause. Don't write this part down right here. Okay, just these guys over here. You can write the prefixes and stuff and get that ready. But I want to explain just this a little differently because I like to write it a little bit differently. What I like to do with my conversions chart and my prefixes, I like to always give the bigger unit the 1. Okay? So if I know between a kilometer and a meter, which one is bigger? A kilometer. So I would like to say 1 kilometer equals 1,000 meters. Okay? Because kilo means 1,000. I don't like to use negative scientific notations that much. Okay, so I like to give the bigger unit the 1, and I tell how many of the smaller unit are in that. Okay, so if I'm looking at decimeters, okay, which is the first one here on my little block, I would say 1 meter is equal to 10 decimeters, rather than saying 1 decimeter is 0.1 meters. Does that make sense? That's the way I like to write it, and that's the way you'll see me do my conversions. You are more than welcome to do it any way that works for you. I'm just telling you how I would write those. So for decimeters, that's how I would write it. I would say 1 meter is equal to 100 centimeters. I'd say 1 meter is equal to 1,000 millimeters. Things like that. 1 meter is equal to 1 times 10 to the 6th micrometers. This is a micro right here. That's what the symbol looks like. It's kind of like a U with a little front tail. Okay, I don't know. I can't even remember what Greek letter that is off the top of my head. And then 1 meter is equal to 1 times 10 to the 9th nanometers. Okay, so that's how I would finish my chart right there. Okay, because I like to give the bigger unit the 1. If you don't want to do that, that's totally fine with me. Okay, but that's how I like to finish it. Because in my unit conversion tables, I like to give the bigger unit the 1 when I'm going between metric system units. I do. If you think you can do it without a T-chart, okay. But that's fine. Or if you have another system that works better for you, that's fine. Doesn't matter to me, but I will always resort to the trusty T-chart. So 193 inches to miles. Are we using the metric system on the first one? No, this is just the U.S. system, so we should know these, right? If I want to go from inches to miles, I might go inches to feet to... you don't have to go meters. You don't have to cross over. Just go from feet to miles, yeah. How many feet are in a mile? 5,280 feet. All right, so I'll show you kind of how I do unit conversions. If I want to get rid of inches and go to feet, they need to go diagonal from each other. Okay, and I always give the bigger unit the 1. Okay, so in 1 foot there are 12 inches, and in 1 mile there are 5,280 feet. So now my units have been canceled. I'm left with miles, which is what I want. I multiply across the whole top, divide by the whole bottom. And I should get a really big number or a really little number? A really little number. Okay, how many miles do we get, Makara? Yeah. Realistically, I don't worry about significant figures in unit conversions because we have a lot of ambiguous numbers when we get to unit conversions. So when we do T-charts and conversions, I'm not as worried about significant figures. Okay, I will tell you when I'm specifically looking at significant figures. Okay? Uh-huh.
Would it be kind of off if we just went straight from inches to miles?
You know how many inches are in a mile?
Well, no, but what if you just multiply 12 by 5,280 and just skip the feet total?
That's fine. Multiply across the whole top. So, hey, listen up, please. So I would take 193 times 1 times 1, and then I'd hit enter in my calculator. And then I would divide by 12, divide by 5,280. Okay? Or if in your calculator you would do divide by parentheses 12 times 5,280. You can't do divided by 12 times 5,280 without parentheses. Okay. All right, so we got about 0.003 miles. Is everyone getting that to come out in their calculator okay? All right, very good. Now we're going to convert from millimeters to meters. So 1382013 millimeters. So I want to get rid of millimeters. That needs to go on the bottom. Do I need to go to centimeters or to decimeters, or can I go straight to meters? Straight to meters. Okay, meters is always going to be our middleman, or the base on the metric system chart is always going to be our middleman. Okay, it's hard to go from millimeters to kilometers in one step. I would go millimeters to meters, then to kilometers, right? So the base is going to be kind of be our middleman. Here, that's where we want to stop, so it doesn't matter. So between these two units, which is the bigger one? Meters, and I know there's 1,000 millimeters in a meter. Okay, so here I multiply across the whole top, which is by 1, divide by 1,000, or I could move my decimal place, 1, 2, 3, which gives me 1382.013 meters. We agree? So which one of those was easier? The metric system one, right? We could just move the decimal place if we wanted to. The metric system realistically is easier because the numbers are all, numbers are all tens. Okay? So the U.S. system only seems pretty easy to us because we're familiar with it. If you were from another country and I tried to ask you to memorize, there's 12 inches in 1 foot. There's 5,280 feet in 1 mile. There's 2.54 centimeters in 1 inch. There's all these kinds of things. That's hard for other people to memorize, right? There's 16 ounces in a pound, all that kind of stuff. Those are hard things to memorize. Whereas the metric system, everything's on a power of 10. Much simpler. Okay? So, but the United States decided no thanks. All right, here's some conversions between U.S. measurements and SI units. So if you don't have those memorized, I would go ahead and put those down. Just kind of a note on our units before we A note on units before we get started with these conversions. Once we start a physics problem, we've got to keep consistent units. So whether we start in grams and convert to kilograms, we've got to make sure we carry that kilograms throughout, things like that. We've got to make sure that we have the entire problem with consistent units. Otherwise, our answer is going to be off by powers of 10. If we're trying to convert density, we're trying to look at density, which we don't really do in physics. But if our density answer is grams per liters, but we're dividing kilograms per milliliters, that doesn't match, right? We've got to make sure that our units are consistent. So if we're given a velocity in kilometers per hour, but we're trying to plug in meters over seconds, same things, it's not going to work, right? We've got to have consistent units. So make sure that you're doing those conversions first so that all of your units match, okay? Match when they need to. How many centimeters are in 3.2 miles? Let's try some conversions here real quick. How many centimeters are in 3.2 miles? This is going to be a mixed conversion. You're going metric system to, you're going U.S. system to metric system. Okay, so when we do a conversion, we're always going to start with what we know. We're going to start with what we know. So we always start with what we know, which means we're going to start with 3.2 miles. What do you think a logical sequence would be here? There's a couple different ways you can go about this, and depending on the rounding, you might get a little bit different answer, and that's okay. Okay? I would go miles to feet, feet to inches, then inches to centimeters. That would be my route. There's other ways you could go about that. You could go feet to meters, meters to centimeters if you want.
Oh, not an inch, sorry.
You could go miles to kilometers, kilometers to centimeters. Okay, so there's a couple ways you can go about this.
I love teaching. I think there's not like 6 steps. I love them. Oh my.
Depending on which route you took and depending on where you rounded your answers, they could be quite a bit of variance here because there's a lot of centimeters in 3.2 miles, so it might seem like our answers are pretty far off. Okay? What'd you get? 990. 0.08 centimeters. Did someone go a different route?
I did. We went from feet to meters. 540,396.
Okay, so he went from feet to meters. Okay? And because our feet to meters conversion might not go all the way out to its complete decimal point, just like our centimeters to inches might not go out to its complete decimal point, we're not getting exact answers. Okay, if I were to measure 3.2 miles and literally count every centimeter, it's going to be somewhere in that range. It's not going to be exactly what we just came up with. Okay, but it's going to be in the range. So this is what we talked about. Depending on rounding, depending on the route you take, I'll look at what your process was. Even though these answers seem pretty extremely different, they're realistically not that far off. Okay. Anyone have questions about how we got to that final answer? All right. Very good. Oops. What's the speed of a bird flying 1.3 meters per second in miles per hour? So we want to convert meters per second to miles per hour. So this one is a little bit trickier. So let's make sure that we get this set up correctly before you get too far into it. Meters per second. Okay? Whenever we say per, that means divide by. So that means we don't put meters per second up on the top. We have to say meters per second. Okay? And we should end with miles per hour. So would you rather convert from meters to miles first or seconds to hours first? Meters to miles, that's fine. Okay? So I'm going to go meters to feet, feet to miles. And you can still all do this on one T-chart. What's our conversion between feet and meters? 1 meter, is it backwards? 1 foot equals 0.305 meters. Yeah? All right. So far we've gotten rid of our meter unit. We've gotten rid of feet. We're left with miles per second. Is that what we want to be in? We don't want to be in miles per second. We want to be in miles per hour. So if we want to go seconds, we can go seconds to minutes to hours, or we can go seconds to hour. The way we can go seconds to hours, we know there's 60 seconds in a minute, 60 minutes in an hour. So 1 hour equals 3,600 seconds. Does that make sense, skipping that one step? You could still go seconds to minutes, minutes to hours, that's fine. Now we've canceled out our seconds unit. And we're left with miles per hour. So I want to make sure that everyone is, listen please, I want to make sure everyone is seeing that T-chart come to its completion. Miles over hours, that's what we wanted. Okay? Divide by the whole bottom and we get how many miles per hour is that bird moving? 2 point what? 2.99. That bird's really good. Okay, so that's not a very fast bird. 2.91. Not going real far. Okay, maybe he's coasting. I don't know. All right. All right. Now I want you to try this one on your own, please. 90 kilometers per hour. I want to find it in meters per second. This is a very, very common conversion that we do in physics a lot. Okay, kilometers per hour to meters per second.